I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics, medicine, nature,
or
Space. Time.
the brain,
Life. The universe.
This week, why did my food allergies improve after a course of antibiotics? Has Earth ever been completely awash and covered with water? And is a protein-rich breakfast less likely to leave you hungry by lunchtime? We're answering your science questions this week. I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Let's meet the panel of people who are going to be answering your science questions for you. David Rothery is a planetary geoscientist. He's at the Open University. What's been floating your boats in the space science realm this week, David?
Well, in space science, we're interested in the developments where NASA and the Russians and the Europeans and Japanese are all saying, let's go to the moon with some space station in cislunar space. But as a geoscientist, I'm also waiting with great interest to see what happens in Bali with the Agung eruption, which has been at crisis point for several days now. 100,000 people have been evacuated. They're waiting for a big eruption.
Tell us, first of all, about the moon thing that you mentioned. Why now, and why is that important?
Well, the International Space Station is good until 2020, maybe till 2024, but it needs to be replaced. So the next move onwards is something in cislunar space orbiting the moon, or a Lagrange point between the Earth and the moon. And there was an agreement signed between NASA and the Russians in Adelaide this week, but the Europeans and Japanese will also be involved. So there's a government space agency-led push to go to this station around the moon as a staging point to Mars. And we're saying, is that going to be the first, or will it be done by private enterprise? Because Elon Musk is unveiling plans for his BFR, which is his big flipping rocket, which is going to get enormously heavy payloads into space and perhaps directly to Mars. So there's competition between private enterprise and governments now, which is great.
So any questions related to space science, they should go David Rothery's way. Sitting next to David is Gareth Corbett. He's at Addenbrooke's Hospital, where he is a gastroenterologist. That means he studies the intestines and how they work. Now, is this true that there are more nerve cells in your intestines than there are in your brain? Is that true, Gareth?
There are certainly more cells in your intestine than in your brain. There are multiple neurons that connect the bowel to the brain, and overall, due to the length of the GI tract, you do have more nerve endings there than you'd find up.
Yeah, how long is the intestine?
So the gut's split into three main parts. You have the upper GI tract, the small intestine, and then the large intestine, which we call the colon. The upper GI tract is around 60 to 70 centimetres in length, and then the small intestine, which is the longest part, is about 6 metres long, varies up to 9 metres in some adults. And then the colon, which I always describe as a vacuum cleaner hose because it can expand and contract. If you get it completely straight, it's around 90 centimetres, but it can be stretched out to up to 2 metres long.
And as a gastroenterologist, you're one of these lovely people who stick tubes into these tubes, aren't you?
That's right. Yeah, that's what I do for a living, yes. It's quite exciting at the moment. There's a development in the world of endoscopy where people can swallow small capsules with cameras in that allow you to look inside the gastrointestinal tract. And the most exciting recent development is that we can now examine the colon with one of these pills. So instead of having to come and have a tube placed where the sun doesn't shine, you can come and swallow a little capsule and it'll take pictures of your colon for you, and you don't have to come to a theatre. You can just go home after swallowing the pill, and then we'll look at the pictures the next day.
Is it big? Is it very hard to swallow?
So when patients of mine first look at it, they often go, "Goodness, that's large."
That's a gulp.
It's about 9 millimetres wide and about 12 millimetres long.
That's quite big.
This is about a little bit bigger than the large antibiotic, but the people very, very rarely have difficulty swallowing them. And if they do, we can help it down with a traditional endoscope.
And how do you get the pictures off?
So the device sends the images by radio waves to a sensor belt, which then saves the images onto a small hard disk recorder that the patient carries around with them for the day. We then put it onto a cradle with a computer, and the video's compressed into an easy reading format, and then it takes about 30 minutes or so to interpret the pictures.
So no need to go filtering through waste products to find the camera again. Does that just go down the loo and get discarded then?
That's right. The one that we use at Addenbrooke's is one where the capsule can be disposed of after it's passed. That's right.
So they're saying, Gareth, you're a hard act to swallow.
Good
to have you with us. So any questions about the intestines, the human body and how it all works, they should go Gareth's way. Sitting on the other side of the room is Sarah Madden. She is a biochemist at the University of Cambridge, and it says here you're doing drugs, but I'm sure that's not not in the sense you're not taking drugs, you're trying to develop new ones, Sarah.
Yeah, that's right. It's very important to make that clear. So I work in making new anti-cancer drugs, but I'm more interested in all drugs. I mean, the research, just to be clear.
What is your approach to making new anti-cancer drugs?
So my approach in my research is we're trying to kind of throw away the rule book and come up with new crazy ideas of doing things. So normally you need to make sure drugs are very small so they can get into all the cells in the cancer cells in your body. But this means sometimes that they have trouble to block certain interactions in your body that can cause cancer. So we're just trying to make bigger drugs, basically.
Any success?
It's working at the first stage, so there's many stages in making drugs. It can take, 10, 15 years. So
it's a long time, isn't it? So you're in it for the long haul. I mean, we had a space scientist on the programme a couple of weeks ago when we were talking about the Cassini mission, and, he was saying, look, it took 7 years for this probe I've been working on for 7 years to get to the place it was going to start working, so it's 14 years of time invested before I actually began to get any data, and I didn't even know if it was going to work when I started. And he said, but that's why we're in the business of doing it, because it keeps it all exciting. David, let's kick off with this one, probably for you. There's a question here from Jamie, who wants to know, when a rocket is returning from space, how much does Earth's atmosphere slow it down?
Okay, well, we rely on the Earth's atmosphere to slow the rocket down. If you're thinking of a re-entry capsule, such as Apollo used, or such as we used to get back from the International Space Station, you have a blunt end and you have tiles to absorb the heat, because the compression when you hit the atmosphere heats the atmosphere so much that you'd burn the spacecraft up if it wasn't properly protected. So you slow down using the atmosphere. It's much easier to land on any planet with an atmosphere than onto an airless body, where you do need to use rockets. But if people have been seeing, is it the Falcon rocket landing back on the barge from which it's taken off, that is using rocket power to slow it back down. So both techniques are used, but you use less fuel if you use the atmosphere to slow you down than a parachute to make the final bit of descent, for example.
Thank you very much, David. And of course, the temperature that you reach is humongous, isn't it? Because you're doing adiabatic compression of the atmosphere in front of the capsule, so you get 1,000 degrees or so.
Absolutely, more than 1,000. I think it's usually described as friction with the atmosphere, but it's not friction. It's not rubbing against it. It's just slamming into it and compressing it. That's why you get. That's why shooting stars are glowing in the sky. It's the compression of the air in front of a grain of dust coming in. It's not friction. It's compressing the air to make it hot.
Thank you, David. Gareth, there's a question here from John, who says, can the bowel grow back after you have some of it removed? For instance, if you have a colectomy procedure. What do you think about that?
The bowel does not grow back after you've had some of it removed. And obviously there's lots of different bowel operations that you can have. So some people have a bit of bowel removed and then they'll have the two ends connected back together again, and some people will have a bit of bowel removed and they'll end up with a sort of dreaded stoma bag, which a lot of people worry about. But we have fantastic nurses that help look after patients and get them used to it, and the vast majority of people with stomas live with them really well. So it's not really something to be afraid of or worried about. It's a consequence of an unfortunate condition you might have had to end up having that surgery. What we do see, though, that is interesting is in patients where they have a limited amount of colon left. For example, in the condition, inflammatory bowel disease conditions, you sometimes have large amounts of bowel removed and then the small intestine is reconnected to a small bit of colon. You do see that the small bowel almost turns itself into colon. There's changes in the appearance of it. It still does maintain a sort of cellular architecture like a small bowel, but when we look at it endoscopically, you get the sort of muscular appearances and things like it's almost reforming, and it helps people stool longer, basically, because the large bowels are still storage mechanisms, so we're not continually having to rush to the bathroom. And if you lose some of your colon, then you will go to the loo more frequently. But the body does adapt to help that change over time after you've had such an operation.
Because people can actually get by with having quite a lot of it removed, can't they?
So you can live without really any consequences without any of your colon at all. So people have had to have the whole lot removed are fine. In terms of your small intestine, that's not quite the case. You can lose substantial amounts of small intestine, but you do start to have nutritional consequences for that. And people with super short parts of gut can start to have liver disease as a result of that. So losing large amounts of small bowel is quite serious. And again, going back to inflammatory bowel disease conditions such as Crohn's disease or ulcerative colitis that people might have heard of, people with Crohn's tend to have often quite significant numbers of operations and bits of small bowel removed. And we do get to a point treating people like that where we say that's enough small bowel removed. We need to try and preserve as much as possible because they do end up having consequences in terms of getting food into them properly.
Thank you, Gareth. Now, Sarah, I understand you have got a bit of a demonstration for us all to take part in to show us something. Talk us through it.
That's
What have you
right.
got in mind?
Someone kind of wanted to know if you can taste food without smelling it. And so the thing is that our tongues have 5 basic tastes. So we have sweet, sour, salty, bitter, and umami. But taste is kind of different from flavour. So taste is when you just put a food on your mouth and you have a chemical reaction and you have one of those or a couple of those sensations that I just talked about. But smell also obviously impacts on flavour. So this is what the experiment is about. So you can't have complete flavour without smell. So that's what my experiment will hopefully demonstrate to these willing participants.
This is a question we got from someone called Lauren who wanted to know how we disentangle the two effects, the smell and the taste. So What have you got in mind? What do you want us to do?
So I have a jelly sweet with me. And the idea is...
One for us all, 3 of us to share?
Yeah.
We get
So
one each?
I have some jelly sweets, yeah.
Okay. Do you want to dish them out
I
then?
can dish them out.
Because David's looking hungry.
Yeah, there you go, David.
I spotted these when we arrived. I've been looking forward.
Do you want one?
I'd love... Yes, please. Yeah.
Chris?
Let's go. Okay.
Okay, so the idea is to split it into 2. So we have, we want to be proper scientists and have control experiment.
Okay, I've got 2 halves.
Okay, so for the first half, we need to make sure we hold our noses very tightly so we can't smell.
Okay,
And
doing that.
I want to put it in our mouths and try and eat it.
Okay, so I'm going to I'm holding my nose, I'm now going to eat the jelly sweet.
Yeah.
What was that?
What's that? Hang on,
flavour you
David. Sorry,
mentioned
David.
umami.
Yeah.
What's umami?
So it's kind of almost a sort of meaty flavour. So it's a kind of, you've heard of like MSG as well. It's glutamate or something that you find in meat. So it's that kind of almost sort of savoury kind of, as I say, meaty flavour that they kind of have sort of just started thinking about, and scientists have only recently discovered that one.
So let's ask Gareth, that you chomping away over there while holding your nose. Could you taste your jelly sweet while you were holding your nose?
No, but I tasted it as soon as I let go of my nose.
Yeah, it's really
David,
interesting.
Similar experience?
Exactly the same. I really was gripping my mouth quite tightly and I could not taste that, and I released it.
Your nose?
As Gareth spoke, my nose, and I was flooded with orange.
flooded with flavour. So Sarah, explain.
So that's that's really good that you guys noticed that. The point is that when we're holding our nose, we can't smell. So all we have is the taste and not flavour. So we just taste the sweet. The sweet sensation is all we experience. But as we take our hands off our noses, then suddenly we get the smell and hence the flavour. So I've given you the second half in case you didn't fully taste it as a little treat and reward for,
Yeah, I'm into that now. I'm
for
now eating that.
participating in the little
I
experiment.
didn't take it much encouragement. So your point is that if you can't get the air flowing down your nose because you're holding it, it can't carry those flavours being sort of volatilised,
Yeah,
boiled off
that's
by the
right.
warmth of your tongue up to where the olfaction, the smelling bit happens in the back of the nose. So as a result, you can't taste, in inverted commas, anything.
Yeah, and it is exactly, and it gives you a sort of understanding of, there's people who can't smell, like people with anosmia, it's called, and so you can imagine what their experiences of food must be like, and it must be
I
very
used to
difficult.
use this trick when I was little because I hated Brussels sprouts. I really like them now, but I used to hate them, and so I found myself when the 5-year-old me discovered if I held my nose, I could eat Brussels sprouts with impunity because most of that strong flavour is very sulphurous compounds that then boil up to the back of your nose and you smell and call that taste.
You're destined to be a scientist, weren't you, Chris?
I clearly was. David.
Sarah, so when we smell as we're tasting, is it because we're breathing out through our nose and drawing air from our mouth into our nose internally, or is our nose smelling what we're breathing out?
I would hypothesise it's a combination, but it's important to also emphasise that flavour is it's also a combination of sight and texture and heat, so it's all things coming together.
Your brain is integrating all of these things together to what we call taste is actually a mixed bunch of senses, isn't it, I suppose? Thank you very much, Sarah. So there you go, little trick, everybody. If there's something very unappetising on your dinner plate, the way round this is hold your nose and then you won't taste it.
Hello, Georgia here with a quick interruption to ask for your help. At The Naked Scientist, we're always trying to make the best possible programmes. And one way we try to improve is by asking you to tell us what you think. The things we're doing well, the things we're doing not so well, and things you think we should be doing but we aren't. We've got a very simple online survey that just takes a few minutes to complete. It's open for the next few weeks, and to sweeten the deal, if you fill it in for us, you could win some Amazon vouchers. The survey is open now at www.thenakedscientist.com/survey. It just takes 5 minutes and is really appreciated. We read every word. Thank you so much. Now, back to the show.
You're listening to The Naked Scientists with me, Chris Smith. And today we've got a panel of experts taking on your science questions. And if you'd like to get in a question to a programme like this, why not send it in? It's chris@thenakedscientist.com. You can tweet at Naked Scientists, or you can find us on our Facebook page as well. And if you are in the mood to look up what we've done in the past on our website, all of our back catalogue of podcasts is there, completely free, nakedscientist.com. Worth a look. Gareth, one for you.
Hey Naked Scientists, I have a question about stress. I realized that how stressed I feel is not necessarily a reliable indicator of how stressed I actually am, and at the same time getting it tested properly is probably expensive and impractical. So my question is, how do I measure this in a practical way in my own daily life for myself? And perhaps more importantly, how do I help my team keep track of their actual stress as opposed to just asking them how they feel today?
So, stress, Gareth, and how we measure it.
So I think stress obviously has physical and psychological sort of outputs, if you like. So physically, we know that our heart rate might go up if we're stressed, or our blood pressure might go up. We might start to sweat. Our pupil size might change. But those are all sort of signs of what's going on the inside, with sort of increased hormones being released, such as adrenaline, and getting us ready for running away. And that's all a bit evolutionary, really, just getting your body ready to fly away. I'd like to dispel the myth that stress is bad, though. So there's a law which is called Yerkes-Dodson law, which is basically like a bell curve that just shows that if you're not very stressed, you won't perform very well. If you're very, very stressed, you won't perform very well. But if you've got a little bit of underlying stress, your performance goes up as that stress increases. So I think that's useful for people to know. Stress is not a bad thing. The question about practical day-to-day stress measurement, I mean, there are sort of scores you can do to determine your stress levels, tick sheets and things, but I did find out that you can get personal fitness monitors that now have stress detector parts on them, like your Fitbit or other electronic device. The only thing about those is it's got to be a bit context specific, because it's just measuring physiological measurements. It's just what's your heart rate doing, how much sweat are you producing, and so on, rather than knowing where you are at the time, because you could just be running at the gym or running for the bus or something like that, as opposed to be in a stressful situation at the time. And the other thing is, we obviously have a way of looking for stress in the real environment, and maybe you could use it at work, which the police use, which is lie detector tests. So they're a way of measuring sort of physical observations to see whether people are lying, which is obviously making them stressed. And they look for minute changes in physiological measurements to determine if someone's not telling the truth. And that's, I suppose, in a way, a very practical way of measuring stress.
They look for galvanic skin responses, don't they? This is little bits of sweat on your skin that changes how well your skin conducts electricity.
And measure your ECG at the same time, and measure your blood pressure during the test, all those sorts of things.
Thank you, Gareth. Now, this one, David, has come in from David, probably for you.
When a star goes supernova and fuses elemental atoms of gold, for example, how do those individual atoms of gold clump together to create nuggets that we can see?
So we better unpack this a little tiny bit. Can you just explain what he means by star going supernova and the fact that gold is in some way bound up in this explanation, and where nuggets of gold come from?
Yeah. Well, hello, David. Well, a supernova is the only situation when you can make substantial amounts of elements heavier than iron. It's the compression waves when a star is so massive it can't support its outer parts anymore. It collapses inwards, gets really dense, and a big explosion blows the outer parts off. When the pressure's really high, you can fuse elements to atoms heavier than iron, among which is gold. Gold's nothing special in this, but gold is among them. Okay, then you've got these particles of all kinds of elements which will be seeding space, and that will form a cloud of gas and dust. And within such clouds is where stars and planets of the next generation of stars form. So the material from which, say, the Earth formed would have a tiny amount of gold in it. But it won't have gold nuggets in it. It'll be isolated atoms of gold. When you formed a planet, it will differentiate. The iron will go inwards, the rocky stuff will go outwards, and in amongst the rocky stuff will be individual atoms of gold. And then geology takes over, and you have processes of distilling the crust, maybe water coming in, dissolving stuff, circulating around, driven by internal heat. And atom by atom, gold's a very inert chemical element, but it can form complexes with hydrogen sulfide and chlorine. But you can get it into solution and then into places where it will come out of solution around some solid initial spec, and then you can grow a gold nugget atom by atom by atom, rarely bigger than a speck of gold, but sometimes as big as a brick. So the gold nuggets don't come from space. They're not formed in a supernova. But the gold atoms are formed in a supernova and get concentrated by Earth's geological processes.
Thank you very much, David. Now, Gareth, we have got this question for you from Olivia.
I suffer really badly from food allergies, but recently when on a course of antibiotics, I could eat whatever I wanted and felt fine. Is there an explanation for this?
So why did Olivia's food intolerances improve after a dose of antibiotics?
It's a great question, actually. So I think the first thing to talk about is what is food allergy and what's food intolerance. So because I find myself explaining this quite often to patients of mine. So sort of probably the most serious type of food allergy is something, for example, a peanut allergy, where you eat a piece of food and you have a widespread reaction to it. You develop rashes, difficulty breathing, and so on. That's a true allergy because the allergy part of the immune system has been activated by eating that bit of food. Then you have sort of in between intolerance and allergies. You have things like celiac disease, which is a condition where a specific part of food leads to an immune reaction, but in a particular place. So it's in the wall of the gut, not causing the whole immune system to go crazy. And then you have intolerances to food. So that's where when we go looking for a problem, we take biopsies from the bowel or have a look through with one of the cameras. We can't really see anything wrong, but people definitely develop symptoms when they eat certain types of food. That's a massive group of people, and those people end up being defined by the medical profession as having functional bowel disorders, which is a term that we use when we don't really understand exactly what's going on, but we can recognise the syndrome of symptoms that are all together. What's probably going on is all to do with the gut microbiota. We have millions and millions and millions of bacterial cells living inside our GI tract, and they live with us, and we require them to survive. They help us digest our food, and they help us sometimes produce important proteins and so on. So they are an important part of our lives. But sometimes things aren't quite right, and the pattern and the types of bacteria that you have growing in your intestine can mean that you don't digest certain types of food in a way that you might expect, and so you end up getting symptoms, and people call them food allergies, but they're almost certainly food intolerances. And what happens normally is the bacteria metabolize the food, they produce gas. Gas stretches the bowel lumen, the tube of the bowel, and that stretch is what sends a pain signal up to the brain and says help. So you take antibiotics, and then you end up killing off some of those bacteria, and probably by chance, in Olivia's case, the ones that were causing her to have a problem, and then she can eat what she wanted. But the antibiotics won't clear all of them. So when she stops, the symptoms can come back again.
Because basically you relapse back to the normal spectrum of bugs that's right for you, or which is normal for you.
Yeah, perhaps. Although you don't always do that. And in fact, what's more common to see is somebody who's had a course of antibiotics and then they end up with symptoms afterwards.
Yes, I've got several acquaintances who've complained of this very problem.
Yeah, and of course the one that's really big in the NHS is this thing called Clostridium difficile, which shuts hospital wards, and it's something that all hospitals have to report on their Clostridium difficile rates and all that sort of thing. But that's sort of an antibiotic-induced problem rather than an antibiotic-preventing problem. There are other things that alter the bacteria in the system, in the GI tract, and one of the things is probiotics. There is actually good evidence that helps irritable
So these
bowel
bugs
syndrome.
do survive the journey through stomach acid, because one criticism is that when you swallow these things, it goes through battery acid in your stomach, which deactivates a lot of these microbes, and therefore the numbers that survive are probably quite small.
That may be true for some of the stuff you buy on the supermarket shelves, but there are some products that you can buy as foodstuffs, not prescribed medicines that contain very high volumes of the bacteria in freeze-dried form, and so they do make it through the gastric transit. But you're absolutely right, large numbers of the bacteria won't make it through that acidic environment.
Where do you stand on transfusion? The whole idea about, capsules, that you pop a pill and it's
so,
a healthy spectrum of bugs to put back in your gut.
Yeah, so
everyone's grimacing. Sarah, you had your hand up just now. Is this something you would indulge in?
I have seen it done. Is it something you sort of, is it freeze dry the poo? Is that right?
Yeah. Have you actively pursuing this, Gareth?
So we did have a what we call a fecal transplantation service at Addenbrooke's. It's
just
it might make you laugh, but the bottom line is that one of my colleagues will thank me for saying this, is stealing his line. The stool is basically its own organ. It's an organ of bacteria. That the main therapeutic use is for treating C. diff that won't get better with antibiotic treatments, and the results are phenomenal for people who won't get better. They just get better the next day after having this. Whether it will end up being a good treatment for things like irritable bowel syndrome and so on, there isn't any data that's firm enough to support that. So I wouldn't support the recreational use of stool tablets, shall we say.
I don't think many people indulge recreationally, do they? I mean, it's going a step too far.
It's in the same way as people take vitamin tablets and things like that, as a kind of lifestyle thing to do to try and make themselves feel better.
Gareth, thank you. We have got this rather nice question, which has actually just come in for you, David, from Jeff.
Hello. I understand how the land masses of the planet rise and fall and change over time, but I'm wondering, was the Earth ever covered just by 100% water with no land showing, and could such a planet exist elsewhere in the universe?
David?
Well, was the Earth ever covered in water? Very definitely yes, if you're prepared to accept water as the substance H2O, because there have been times when the planet has been covered entirely by ice. That's both the land masses and the oceans covered by ice from pole to equator. These are called the icehouse world conditions, the most recent of which was about 635 million years ago, so just pre-Cambrian, just before large amounts of multicellular life. So extreme climate events covering the Earth in solid water, yes. The question was probably thinking about liquid water. Now, land masses don't so much rise and fall as at the moment continents split apart and rearrange themselves. And the amount of continental material is scarcely changing over time. But if you go back about 3 billion years ago, there wasn't much continental crust, maybe just a few ocean islands. And so virtually the whole planetary surface would have been covered by liquid water at those times when it wasn't frozen. So very deep in the past, a few islands in amongst global oceans. That's as best we get, close as we get to a planet covered in liquid water. Can they occur elsewhere? Yes, there are certainly many worlds in this solar system, moons of Jupiter and Saturn, which are ice at the surface, rock underneath, and maybe an ocean sandwiched in between. But to go to bodies covered in liquid water, well, these are known as water worlds, probably from the science fiction movie. But it's an obvious term. We think planets that are rocky but have a greater mass than the Earth, twice to 10 times the mass of the Earth, are going to have so much water as well that by the time the water's squeezed out of the rock, it's going to be such a deep ocean that you'll never have land masses sticking above the surface. So we are expecting to find water worlds among the exoplanets. And we've got planets round 2,000 or 3,000 stars now. Most stars in our galaxy we know have planets now. So some of them are going to be water worlds, and we think we're identifying some of them by their size and their mass.
So if not this one, definitely somewhere out there, maybe a planet or a galaxy far, far away. David, thank you very much. You're listening to The Naked Scientist with me, Chris Smith, and this week we're answering the science questions that you have been sending in. We've got space scientist David Rothery, biochemist Sarah Madden, and gastroenterologist, gut doctor Gareth Corbett. Well, it's time now for a little bit of a quiz, and of course you can take part at home too. It's in 3 rounds, and you can confer. And we're going to have 2 teams. We're going to have Gareth and David, and Team 2 is going to be Sarah. And because we unfortunately had one person short this week, Sarah, we found you somebody. Vinny has kindly agreed to pop in, and Vinny's going to be your sidekick.
Hello.
How's your science, Vinny? Is it good?
I'm sorry, I'm not going to do well for you here, Sarah.
Moral support, probably.
Yeah, I'm
but you're
very
big
grateful.
enough brained, Sarah. I'm sure you're going to cope adequately well. Okay, right. So basically, I read you the question, then you can decide, you guys, whether or not it's a right or a wrong. And if you get the answer right, you get a bing. If you get it wrong, you get a bong, of course. And the person who gets the highest, or the team that gets the highest score, goes away with a prize. A prize beyond price, I was going to say, which, you go away with your reputation intact. The Naked Scientist Big Brain of the Week. Okay, here we go. Team 1. This is Gareth and David. Your first question, it is, what number is opposite the number 3 on a dice?
It always adds to 7, we think. So, yeah, we're agreed it's
4.
4. Yeah. Wow, they're off to a good start. It is
I
indeed
was
4. Opposite sides on a die
question.
always add up to 7, as you quite correctly say. Well done, you two. Right, okay. Vinny and Sarah. If a bat and a ball together costs £1.10 and the bat costs £1 more than the ball, how much does the ball cost?
£1.10. Because if it costs 10p and it's
Oh, yeah,
pound
sorry.
more.
The bat costs a pound more than the...
Yeah.
I can do this.
What's your answer?
I'll let you take the flak.
That's very gentlemanly of you, Vinny.
I'm sorry, this is so stupid. We can just sacrifice it. I'm sorry. I know it's really easy, and my simultaneous equations are just going out.
It's actually a trick question, because of course it's 5p, because you add £1 on to get £1.05 for the bat, so the total is £1.10. Yeah, I fell for it too, Sarah. When I first heard that a few years ago, it's the gut reaction immediately, you get it wrong. Anyway. That's good. We've got David and Gareth out in the lead at the moment, and back to you two. So your question, the 2017 Nobel Prizes are in the news at the moment, and with that in mind, we would like to know what the Swedish scientist Alfred Nobel, after whom the prizes are named, is famously credited with inventing. What do you think?
It was dynamite, wasn't it? I was worried you were going to ask me who'd won the prizes this year, and that would have shown us up awfully. But I think he invented dynamite or some explosive.
I'm happy to go with you.
Well, we better go. What was he famous for, is the question.
Yep.
For inventing dynamite.
You're on fire, a bit like his dynamite, okay? It was indeed dynamite. In 1867, Nobel invented dynamite. It was originally sold as his blasting powder, but he decided to change the name to dynamite after the ancient Greek word dunamis, which means power or strength. So they knew all about branding, even in Nobel's day. So 2 points so far to David and to Gareth. Right, let's see if you can salvage your reputation a little bit, you two.
I'm just so annoyed with myself, but it's fine.
In 1901, a group of divers discovered what is believed to be an ancient analog computer made from an intricate combination of gears. It could predict eclipses, but what was it called?
I have no idea. I thought
Want to have a guess? Is David helping you?
Yeah, he's cheating. I don't know it, so I can pretend to play
Hang
it
on
cool.
a minute. What have you
I
written?
can't read his handwriting.
I'll give you David, what have you written?
I've written Antikythera mechanism.
Yes, it is the Antikythera. So +1 to this team for the correct answer, -1 to the other team for cheating and helping, because
Let's
that's
go
not
with
in the
that.
rules. So the scores are even. So now we have an interesting position because everyone is on the same score. So we're into the final round. Everything to play for. Isn't that good? I'm so glad you cheated, David, and enabled me to dock your point. Bit of detail about the Antikythera. It dates from 205 BC to maybe 70 BC. Experts think it was designed by Hipparchus, who's considered to be the founder of trigonomics because it uses his theory to track the motion of the moon. So it was an ancient timekeeping and celestial prediction computer. Right, Team 1, Gareth and David. True or false, the Mongolian pepper mouse is a small rodent that lives in Central Asia, and it has a defensive ability to spray saliva that contains certain capsaicinoids, which are the chemicals that make chilies pungently hot and burning. What do you think?
Sounds like the sort of thing that would be true to me.
It's probably a trick question. It's not in its saliva. Yeah, go for it.
We'll say true because it sounds plausible.
No, we completely made that one up, actually. There is no such thing as a Mongolian pepper mouse. But We did cover on this programme back in 2006 the discovery by David Julius from University of California, San Francisco, the discovery of a component of the venom of a certain type of tarantula that does activate the very same receptors as capsaicin, which you find in chilies. So when you get bitten by the spider, it burns in the same way as if you'd rub chili peppers on your wound. So no points to you so far. Let's see if you're going to end the day level pegging or if the other team can snatch victory from the jaws of near defeat. OK, over to Sarah and Vinny for question 3 for you. In humans, the longer your fingers, the faster your nails grow. Is that fact or fiction?
That doesn't seem like something that should be right.
No, I don't. So if your fingers are longer, I think it'll be further from your... I mean, it's a greater distance, so they'll grow slower.
You're going for slow, so you think it's the wrong way round. You're going for wrong.
Yeah.
Yeah.
No, actually, it's true. In mammals, the rates of nail growth are proportional to the length of the terminal phalanx of the digit. That means the end bit of the finger beyond the last joint. And so your index finger nail grows slightly faster than your small finger nail, and your fingernails grow about 4 times faster than your toenails. And your nail's average rate of growth is about 3 millimetres, which, as a geologist David will know, is roughly the same rate at which the continental plates of Eurasia and America are moving apart because of seafloor spreading. So there we go.
It also explains why I don't have to cut my toenails as often as I have to cut my fingernails.
That's right. Yeah.
I've been observing this as a phenomenon, thinking, surely I've got to cut my toenails as well. And
Ever
now I
the
realise I
scientist.
don't have to, and I understand why now. It's brilliant.
Wonderful. I'm glad we educated you. Thank you. And that also means that no one goes home the winner. Where everyone's even Stephen, so that's wonderful. Thank you very much. And thank you, Vinny, very much for stepping in so well. We're
You're
very
welcome.
grateful.
I treasure myself on knowing absolutely nothing.
Well, at least we had an even balanced team, didn't we? Thank you, Vinny. Gareth, a diet-related question for you.
Is it true that a protein-rich diet can help you feel more full?
So should I be front-loading my day with a protein-rich breakfast in order to defer hunger pangs at around 11 o'clock?
There is medical evidence that shows that a higher protein diet will make you feel fuller for longer. That's been done in a meta-analysis, so that's a study of lots of different studies to be able to tell us if that's the case. And that was based on looking at what people ate, and then they scored their fullness in these various studies. And so that's been shown to, yes, it does make you feel fuller longer. But the more interesting question is actually, why does it make you feel fuller longer, rather than the does it or does it not? Because actually anybody who's a regular bodybuilder would answer that question of, yeah, of course it does, because that's what I do for my diet. But there is some science behind this. So first of all, just to think about how protein digests, because proteins are complex molecules made up of lots of amino acids, and as you break them down, they become polypeptides, which are slightly longer chains of amino acids, and peptides, which is 2 or more amino acids, and then you have amino acids on their own, and they're basically the building blocks of life. So we have to eat protein because that's what most of our cells
It's what
are
we're
put
made
together.
of, isn't it?
It's what we're made of, exactly. We eat protein in the form of meat, eggs, for example, and our body starts to break it down in the stomach with enzymes until it gets to its most simple form, and then it goes into this circulation through the wall of the bowel up into the liver, called the portal circulation. Now, the portal vein is a really important blood vessel. It carries basically all of the stuff that goes into our mouths into our circulation via the liver, which is like a big factory in the body. It does lots of stuff. It seems that along the portal vein, there is a type of receptor, which is like a little sort of plug socket, if you like, which seems to be activated to say, I feel full, I'm satiated. And it seems that might be the mu-opioid receptor within the portal vein, for those of you that are a bit more interested in it. It seems that by protein binding on those receptors, you get an effect where the brain goes, oh, okay, I'm now fuller. So it seems to be something going on in the portal bloodstream as opposed to something going on in the GI tract, which is actually really interesting.
So would the ideal breakfast then be something like egg? Because people always used to say, go to work on an egg. That's got a lot of protein in it. So would that be a good choice to have then?
Well, based on the stuff that, on the fact that we know that protein makes you feel fuller longer, it should keep you locked up till lunch, if you like, better than Shreddies, which is a carbohydrate breakfast.
Yeah, so what effect does that have? If you have a cereal-rich, very carbohydrate-rich breakfast, often people add a bit of supplementary sugar as well to that. Does that end up sort of leaving you with a rebound hunger pang later?
Yeah,
likely?
and they pour fat over the top as well, don't they, in the form of milk. So.
Well, there is that. And then there's the whole kind of fruit juice that goes with it, big dose of sugar with that too. Yeah, I mean, is there an impact of that?
Yeah, so carbohydrates are definitely processed much quicker, and carbohydrate diets, you do feel fuller for less time. time compared to protein. So if you wanted to stay fine till lunch, then I would have thought an egg is a reasonable thing to eat
So
for breakfast.
omelette, scrambled egg and boiled egg.
And
There you
bacon.
go. I'm doing my bit for the egg industry with a bit of bacon on the side. There you go. That's Gareth's prescription for as a gastroenterologist
For breakfast.
a good way to start the day. David, let's try and sneak this one in very quickly.
Hi, Chris and the Naked Scientist team. This is David from the Shetland Islands. My question is, why has there been no planet formation where the asteroid belt is located? Would the gravitational pull between the Sun and the planet Jupiter be responsible for a planet not being created?
So, David, another David with a question for you. What do you think?
I think you're pretty much on the ball there, David. Most scientists are pretty sure that it was Jupiter that stopped a planet growing where the asteroids now are. There clearly was planet-forming material all the way from near the Sun outwards to Jupiter and beyond, and it would clump together into larger and larger bodies, eventually planet-sized bodies. But too close to Jupiter, and Jupiter's gravity would stir up the orbits of the bodies just inside its orbit, which is where the asteroid belt is, and cause the collisions between such bodies to be too energetic to allow material to clump together. So no very large bodies grew. The largest bodies there today are less than about 1,000 kilometres across. So they're stirred up, and most of the material there, in fact, has been lost because of Jupiter. We couldn't make a planet now if we stuck all the asteroids together. It's about 100th of an Earth mass in total. It's a surprisingly small amount, even though there are thousands of bodies there.
Where's it all gone? Has it become asteroids and impactors that rain down on us in the early phases of the solar system then?
Well, if we've lost about an Earth mass or more of material from where the asteroid belt is, a lot of it's been scattered out of the solar system, some scattered inwards and would have hit Mars and the Earth and Venus and Mercury. And doubtless some has been gobbled up by Jupiter, which would scarcely notice it because Jupiter is 318 times the mass of the Earth. But Jupiter has stirred stuff up, and that's what stopped a planet growing between Jupiter and Mars.
Thank you very much, David. Right, let's get on with some more questions.
This is Ken Schaefer from Rice Lake, Wisconsin, USA. I was wondering, who is my closest genetic relative? My parents, my children, or my siblings? Thank you.
Sarah, what do you think?
That's a really interesting question. I think short answer, it's a little bit complicated, as many things are in science. So you are 50% related to your parents, each of your parents. You are 50% related to your children. When it comes to siblings, it's, if we're being all scientific about it, it's 50% on average. The reason that is that when you inherit the DNA from your parents, each chromosome that you have from each parent, there's a bit of scrambling. So if you're comparing different siblings, they could take different parts of that chromosome, and so it's possible for you to be taking the same parts or completely different parts, and so that's why it's 50% on average. But I think it's kind of cool to remember that this is relatedness and not the genetic similarity. So that would be the bases, the different bases that make up your DNA, because us humans, even just two random humans, are 99.5% the same in terms of sequence, the DNA sequence. So basically you and your family are, if you're going to estimate, are 100% the same, which sounds crazy. But I think it's also really shows evolution in the fact if you take two random things like a banana and a human, they are 50% the same in terms of the DNA sequence. Obviously, this is not relatedness. We're not saying we're related to bananas, but the DNA sequence.
So the chemical recipe book in our cells is basically 50% of the genes that are running a banana cell are also being used in your cells to make your metabolism work as well.
So the DNA is crazy. Like, I mean,
it is, isn't it?
Because
but not that you're related to a banana or anything.
No, especially after the quiz, you may think I have.
Thank you very much, Sarah. You're listening to The Naked Scientists with me, Chris Smith. Now, it's a Q&A show. That means you're sending in the questions and we're trying to answer them. If you'd like to get a question into a programme like this one, then you can send it in to chris@thenakedscientist.com or you can tweet @nakedscientists. Now, we've got this question here for you, Gareth. What do you make of this one?
What is electromagnetic hypersensitivity and how does it affect the body?
So what on earth is it, first of all?
So electromagnetic hypersensitivity is the production of symptoms of all sorts that people complain of as a result of an exposure to an electromagnetic field of some kind. So that could be such as something produced by an electricity pylon, or a Wi-Fi network at home, or your mobile phone next to your ear. And people are describing things like headaches, nausea, aches and pains, all sorts of different things, visual disturbances, taste disturbances as a result of exposure to electromagnetic fields. It's a bit controversial because the symptoms are pretty non-specific and they're not reproducible from person to person. And there's no, unfortunately, scientific basis that's been discovered to support the hypothesis that electromagnetic fields cause symptoms in people.
So have people done trials where you do a blind trial, you put someone in an environment and expose them or not expose them, they don't know who's being exposed, you don't know who's being exposed, and you look at the symptoms and see if there is a correspondingly good history?
Yeah, that's right. So they've done it in a number of different ways. One way is the most basic, in that you put somebody in a room and they try and tell you when they think the electromagnetic field is on or not. But probably more interesting than that is the concept of a sort of nocebo study, which is where you it's not the nicest thing to do, but you trick the person to think they're being exposed, but they're not. So you tell somebody the box sitting next to them is emitting an electromagnetic field, but it's actually a sham, and then they tell you that they've developed symptoms. So there really is nothing scientific to support the concept of electromagnetic fields causing symptoms in people. That said, it isn't something to completely poo-poo about in the medical world, because we do put devices into people, such as pacemakers, and that people do have to think about electromagnetic fields that they might be exposing themselves to if they have one of those devices in.
Gareth, thank you. Quick question here from Braden, who says, how do electric eels get their energy? Well, the answer is they use modified muscle cells. They're called electrocytes, and they are strung together along the inside of the fish in the same way as that if you connected a battery end to end and you connected the plus of one battery to the minus of another, the voltages add together. So these electrocyte cells slowly accumulate voltage, and over a very big eel, you maybe get 500 volts, and they're discharged from just below the chin of the eel and its tail. And so the eel is basically a giant accumulator or battery, and it's pumping ions of sodium and potassium in and out of these cells to generate those tiny voltages, which together, over the course of these thousands of cells, sum to make those hundreds of volts. Right, here's a question for you, David.
Hello, Naked Scientists. This is Renee from Germany. I've heard that Saturn's moon Titan has many of the required building blocks for life. Yet its extreme cold allows methane to exist in liquid form instead of water, and helps Titan retain its unique dense atmosphere. My question is this: when our sun becomes a red giant, will this warm up Titan, and if so, what will happen to it? Could it become warm enough for life to develop? How warm could it get before losing its methane lakes and its atmosphere? Thanks.
And could we go and live there? Minus 200 or so at the moment, but it might warm up a bit. What do you think, David?
Well, there are many parts to Renee's question. I mean, Titan is already warm enough for life if you go inside of it to where we're pretty sure there's an internal ocean of liquid water, because we know the surface is decoupled from its core. They rotate at slightly different rates. So inside Titan, you could have Earth-like life, or the kind of life we get at hot vents around the Earth's ocean floor, even at the present day. To answer the question about what will happen when the sun warms up towards a red giant, which won't happen for about 5 billion years, so no need to worry. Yes, Titan will warm up and probably not be swallowed by the sun, so it will still be there. But it doesn't need much warming before Titan will lose its methane lakes. I think if the surface temperature rises by about 5 degrees, that methane will all be lost. It's just on the cusp of being liquid on Titan. It's the only body apart from the Earth that we know of which has a liquid phase at the surface, which will rain out of the sky and form rivers and pool together in seas and lakes. It's a marvellous place. So, but well before the sun has swelled up to a red giant and burnt the Earth away, Titan will have lost its liquid methane at the surface, and most of the methane then will also be lost from the atmosphere, I expect, because it will be broken down by ultraviolet light into hydrogen, which will escape, and carbon, which will react with something or other. So it will have lost its methane. Will it become a body that we could go and live on if the Earth's uninhabitable? We'd have to live on the rocky remains of what's inside, which may be buried in too much water. It rather depends on how much of that water is then lost. So if we're still around in 5 billion years' time, we'll have ways to travel from one star to another, I would hope. Otherwise, what have we been wasting our time doing? I don't think we'll be looking to cling on by evolving into something which can live on Titan.
So maybe not a home from home then, but certainly an interesting place to study. Thanks for that, David. Well, that's all we've got time for this week. Thank you to our guests, who are David Rothery, Sarah Madden and Gareth Corbett. The programme was put together by Tom Crawford. Do join us next week when we're investigating DNA, ancient and modern. And towards that aim, we've even sequenced a sausage. The Naked Scientist comes to you from Cambridge University. It's supported by the STFC, the EPSRC and Rolls-Royce. I'm Chris Smith, and thank you very much for listening. Until next time, goodbye.